everyone. So moving into Unit 4, Lesson 2, I will apologize in advance for the length of this video because it's probably going to be fairly long, but it is kind of the brunt of our objective for this unit is looking at actual functions and what makes something a function, the domain of that function, and all of that. So how to determine if it's a function, and then how to evaluate those as well. In nearly every physical phenomenon that we observe, one quantity depends on another. We use the term function to describe this dependence. So, for example, height is a function of age, cost of mailing is a function of weight. All right, your height depends on how old you are, at least to a certain limit, and we could talk about that as well. And then cost of mailing is, again, a function of the weight of the package when we're talking about shipping packages or mailing even letters if it's an overstuffed envelope. Now, at a certain age, you would reach your top height, as it were, and then sometimes, often, you hit another age and you start to kind of lose bone density and you begin to actually go backwards. And so that function graphed over time would look fairly interesting, but your height is dependent upon your age. So rules that assign each input or each element of y to exactly one, excuse me, I said that's backwards. Each element of x to exactly one output, or f of x, is what you're looking for here. And remember, f of x is just your y term. And so you put in an x value, you get out a y value, right? The set of all x's is your domain, and this is your independent variable, what you don't have control over. And then your set of all y's is your dependent variable, or your range. So you have your domain and your range. So determining if something is a function is looking to see if it has that functionality. Does it have exactly one x for each y? So in other words, do any of your x values repeat? All right, so you look at your relation and you determine, does each of these x values have a y value? And in this case, yes. 5 maps to 3, 9 maps to 17, 14 maps to -4, and every single one of those has exactly one y value. So this is a function. Where if you look at a mapping for the second one, for example, you can see, well, 5 maps to 3, 9 maps to 17, 14 maps to -4. Well, 5 also then maps to -1. And so as soon as I have that number, that x value mapped now to 2 numbers, my x values have repeated. And this one doesn't repeat. And so this is no longer a function. So this is not a function. So remember, not all relations are functions. You have a function if no x values repeat. And so we can test that with, we can test that on a graph of a function instead of just a relation by doing what's called the vertical line test. And so look at your graph. If any vertical line would touch more than one point of your graph, then it is not the graph of a function. Now, that doesn't mean it's not still a relation. We still can obviously graph it, or you wouldn't have the graph at all, but it's not a function. Okay, so for example, here we can draw this line here. Well, it hits right here and right here. So that would be like if I map the relation, this point is at, let's say, -1, -1, and this point up here is at -1, 1. And so that x value, and I'm writing in a color that most of you probably can't see, but this x value is repeating here, right? So it's happened twice. So this is not a function. All right, where this one, if I draw these vertical lines going here, and even though it looks like when I get here that maybe this is horizontal, it is changing, and you can kind of hopefully see it is changing ever so slightly. And so if you would, well, let me zoom in right now. If you would be really careful when you're graphing things like this, especially like parabolas, don't make it a straight vertical line, or then it no longer is a function. But this one passes your vertical line test, so it is a function. All right, this one again does not pass your vertical line test, so it's not a function. All right, so real quick test of a graph can tell you if it is or is not a function. When you're moving into equations, you can go ahead and try to graph them on your graphing calculator. Solve for y, decide if x goes to one y or multiple y's, and then you can determine if it is a function or not. So for this one, you have x squared plus y equals 9. So y equals -x squared plus 9. You should, from Algebra 2, be fairly familiar with these types of graphs. This would be a quadratic, so it would graph something like this. And so you can see that every x has its own y. So even though your y values repeat, right? I have y equals 0 twice, y equals 1 twice, y equals 3 twice. Even though those y values repeat, every x has a y, so this is a function. So this is a function. All right, you can type that in your graphing calculator. We will use those quite a bit in this unit. Or you can just keep plugging in numbers and see if your x values repeat for a while and test it that way. Whereas for this one, for example, if we solve for y, we get the absolute value of y is equal to -2x. Well, in order for this to be true, we have to remember our rules for absolute values. This y value, or this side, excuse me, and not the y value itself, but this side will always be positive. It's a distance. So because we're talking about this always being positive, that means that this x value, because of this negative, in order to make this true, in order to make that absolute value always positive, every x must be negative. All right, so then you're looking at a table that says, okay, we have x and y. If I plug in a -2, well, the absolute value of y then equals 4. All right, because I have -2 times -2. Well, there are two numbers, right? The absolute value of 4 is 4, but the absolute value of -4 is also 4. So y could be plus or minus 4. So -2 results in 4, but +2 would also result in 4. Or excuse me, -2 could also result in a -4 for my y. I said that backwards. Okay, so if I'm looking at my x's, both -2 and -2 could mean that y is either 4 or -4. And so my x values have repeated. This is no longer a function. And if you graph that, you would see that this is, in fact, a sideways absolute value. It goes this way. All my x values are negative. So that doesn't pass the vertical line test. Okay? So just keep that in mind. It has to pass the vertical line test. No, nothing can repeat. All right, reminders of function notation. Common names, you might have f of x, g of x, h of x. This, how we're reading it, f of x or f at x, I will pretty much consistently and always use the first. All right, this is not a variable. You're not solving for f, right, or g or h, okay? Your general formula rules that apply to many x's are still there, okay? This tells us what to evaluate for. You want the function at whatever is inside of your parentheses. So whatever is there, you're plugging that in for your x value or for your t value or for whatever. All right, so if I have h of t is equal to t plus 1 over t, and I want to find h of 1 over x, then I'm going to replace each of my t's with 1 over x. So this is 1 over x plus 1 over x. And that means this is then 1 over x plus, keep change flip, x, right? Well, to add those together, I need a common denominator, so I'm going to multiply by x over x, and I'm going to get x squared over x. And then I have x squared plus 1 over x as my final answer. All right, go ahead and try to evaluate for the next two. Okay, so hopefully you got 5 over 2 and then realized with 0 on the bottom here, this is a domain restriction, and I'm just going to abbreviate that DR, so it is no solution. Okay, so being able to plug in and evaluate anything for a function, whatever is in those parentheses. So whether it be a number or an entire expression, you're evaluating for that. So I would like you to go ahead and try the same thing here. Just plug in and solve. Okay, and checking those answers there, I just want to pay careful attention right here. Make sure that you are actually foiling this out and not distributing that square. Okay, so FOIL, distribute the 3, combine like terms, and you get your final answer with that. So it doesn't matter, again, whether we're plugging in just a number or we're plugging in an expression. We simplify using our rules of exponents that we always have from Unit 1, from Algebra 2, really. Okay. So just remember, and again, I'm kind of going to go fairly quickly here. This video is going to be long anyways. A function is defined by a formula. So this one is defined by x squared plus 4. Express in words how f acts on the input x to produce the output. So what happens when we plug in x? Okay, so what are we doing to x essentially? What are your order of operations? So you would just answer this question, and this might be a good test question, would be just what are you doing here? You are squaring the x value, then you are adding 4. So what we are doing with our input is squaring x, then adding 4. And so every single time, so on B, that's how we evaluate these. If we're taking f of 3, what is the function at 3? Well, we're going to square 3, so 9. And then we're going to add 4, so 13. All right. F of negative 2, we're going to do the same thing. We're going to square negative 2, which is positive 4, and then add 4, so we get 8. All right. F of the square root of 5. Well, we're going to square the square root of 5, and when we square a square root, they cancel, and then we're going to add 4, so we have 5 plus 4 is 9. All right. So again, looking at what is the input, what are we doing to it, now what is the output? All right. You can also find the domain and range of this, and you can look at a graph for this if you want to find the domain of that. Remember, your domain is a set of all x's. It's not just the x values that you plugged in. So this graph's a parabola, and it's about knowing those parent functions and where they've shifted. So it graphs a parabola plus 4, and so this would be the 4 value, right? And so this is the minimum value of my range. Well, my x value covers everything. This parabola is just going to get wider and wider and wider, so it covers the entire x-axis. And so for parabolas, the domain is all real numbers. Or we can put that in interval notation and put negative infinity to positive infinity. The range, though, is starting right here. This is our bottom value. There's nothing less than 4. And so our range is starting at 4 and then going up, because we're moving into the positive direction here. We're moving towards infinity. And so noting what would that graph look like, or what are those values that work for x, and then what do they get us for y? Okay, what is our input, what is our output, and what is that set? Okay. Now this last one, you're evaluating what's called a piecewise function, and a piecewise function has domain restrictions set on it. So these are domain restrictions. Okay, and domain restrictions essentially mean so for this piece of the graph, all of the x values have to be less than 0. So these are domain restrictions. So all of that being said, when you are evaluating a function like this that has domain restrictions, you want to make sure that you're plugging those values into the right section of your graph. And so f of 12, for example, if the x value is 12, where does that fit? Well, 12 is greater than 2. And so here we're going to plug in the f of 12 to this function here. All right. F of negative 9 fits here. So we're going to plug in the negative 9 there. All right. F of 1/2, that fits in between. So that gets plugged in here. And so what I mean by plugged in is this is the function within this domain. Okay. So when I'm plugging in negative 9, I'm going to do 3 times negative 9. And so I get negative 18. And this is f of negative 9. Okay. When I do f of 1/2, I'm going to do 1/2 plus 1. And so I get 1.5 or 3/2. And I write most things improper. And then when I do f of 12, I'm going to do 12 minus 2 and then square it. And so 12 minus 2 is 10. Squared is 100. Okay, and I repeat that for any time I evaluate. This one says f of 0. Be careful with that one, because this is less than 0. This is less than or equal to 0. And so the f of 0 actually goes here. F of 0 is going to be 0 plus 1, so 1. All right, finish that out. Okay, so the 2 goes here because, again, it has that equal sign. And then the 6 goes down here because it's bigger than 2. Okay, so again, understanding where do I plug these values in at? that will be the biggest help to you. Okay. So going on with domain and understanding restrictions, even under radicals, we have domain restrictions. So you're looking at denominators or under radicals, and understanding that X values or domain have limits, because sometimes it gives us undefined, or it gives us something that just doesn't make sense. So, and we do need to stress here even radicals. We can take, what numbers can we not take square roots of? And so we're looking for restrictions, okay? So we've done rational function domains before. If you have, go ahead and practice, because we've done this already, finding the domain for this function. All right, so our hole in our graph would be at 2, because that would be what makes this undefined. Well, square roots work the same way. And so for like this one, if you have the square root of 7 minus 3x, well, underneath this radical needs to be greater than or equal to 0, because otherwise we're taking the square root of a negative number. And so if I solve just that portion out, then I know that negative 3x needs to be greater than or equal to negative 7. So x needs to be less than or equal to, remember your inequality rules there, 7 over 3. Well, what does that look like on a number line, right? If this is 7 over 3 and I can be less than or equal to that, well, then I have a solid circle at 7 over 3 and I'm going this way. Your domain is that interval, so I need to describe that interval. Well, I'm going from negative infinity all the way to 7/3. Here's where we need to go back to unit 1 and interval notation. We're going to actually use a bracket on this one. Notice up here we used parentheses. That was the whole. This is the stopping point for our domain. We can't have anything over that, but we can have exactly that. And so think about, go back to your unit 1 note if you want to, and review that, okay? This last one, and often the top of a function doesn't matter, but because square roots have domain restrictions, this square root being on the top creates a restriction. So I need to find both my restrictions for the top and the bottom here. Well, the top just means that if I have the square root of x and it needs to be greater than or equal to 0, that x itself needs to be greater than or equal to 0. Okay, so that's one of my restrictions. If you think about that on a number line, right now I'm saying, okay, well, if I'm at 0, it needs to be from here over already. Okay, but I also have restrictions on the bottom, so I need to factor this. All right, well, 2x squared plus x minus 1 breaks down into 2x minus 1 and x plus 1. And I'm not going to go back over that factoring. You're expected to know that by this point. All right, keep in mind that neither of those can equal 0. Well, that means that x cannot be 1/2 or negative 1. Again, not going through how I got to that. That's solving these factors, so go ahead and do that. So on your graph, you have a hole at negative 1. Well, that's okay, because I have to be greater than 0 anyways. Otherwise, it messes with my restriction on the top. But you also have a hole here at 1/2, because it can't be that value either. And so when you're describing your domain, you have this little bitty interval right here. You have to skip over the 1/2, and then you have the rest of this interval right here. Okay, so we're starting at 0 with a closed circle. That's the smallest number we can have. And we're going to 1/2, but we can't include that, so there's our parenthesis. We're skipping it, so we pick up back on the other side of 1/2, and then we approach infinity. All right, so that is your domain for this. Okay, and just due to the length of this lesson in general and trying to keep videos somewhat short, I'm going to stop this lesson here, and then you'll pick it up in part 2, and we'll continue on with how to graph these functions.